Hello, welcome to another maths tutorial video. By the time you've made it to this video, I'm expecting you've come across factorising on multiple occasions in your maths education. There is of course the classic highest common factor style of factorising, and then separately there is of course factorising quadratics. The problem I've encountered though is that students, after seeing those types of factorising, do begin to view factorising as this very specific thing that only happens in very specific scenarios, rather than as a tool that can be used to solve a wide variety of different equations. Therefore, that is what we're going to be looking at in today's video. As a result, I wasn't entirely sure when planning this video exactly how to pitch it in the context of your wider maths education. And that's because although on one hand I'm a firm believer of it's a good idea to get people into good habits early on, at the same time it's easier to apply something to a variety of topics once you've actually studied a variety of topics. But I have tried to make it the best of both worlds today, because although we are going to be applying factorising to a whole variety of different topics, I'm going to be only concentrating on that initial stage of how do you know whether you can factorise or not and how do you do it, and not the steps afterwards. So even if you haven't come across some of the topics we're looking at in today's video, you can still hopefully understand how factorising can be useful in these situations and see how we can do it. So with all of that said, let's get started. And the first bit of advice I've got to give you is that factorising is mostly only useful when an equation has been rearranged to be equal to 0 first. There are some exceptions to that, but they are very rare, and we'll come across and deal with those situations when they become important. But it's therefore good to just go in at the beginning with this idea that if you want to be using factorising, first rearrange the equation to make it equal to 0 before you try it. So an example for that would be this thing here, because the problem is it's very easy for students to look at the left hand side and get excited because they go, oh my goodness, it's a quadratic, and oh my goodness, I could factorise that. Of course it would factorise to x minus 2x minus 3, but although you can do that, it wouldn't be helpful because the equation is not equal to 0 yet. So if we're trying to solve the equation, factorising before that situation is not helpful. So first what you want to do is move everything onto one side of the equation before you start trying to do any factorising. So I've taken away the x and taken away the 22 to move it all to the left hand side. Then we can do some algebra simplification. The minus 5x and the minus x make a minus 6x, and the plus 6 and the minus 22 make a minus 16. And now the equation's equal to 0. This is the moment when we can start considering whether we can use factorising to solve the equation, and the answer is yes, it's a quadratic and it is one that factorises, so let's factorise it because then it'll be an equation we can solve. In this case it would factorise to x minus 8, x plus 2, and then from that the reason we want to make sure equations are equal to 0 before we can factorise them is because then each individual factor can then be separately set equal to 0 as their own mini equations to solve. Basically, factorising allows you to split one big scary question up into lots of smaller bite-sized equations that are easier to solve. So therefore, for instance, for this particular question, the answers are x equals 8 or x equals minus 2. So that's the first thing to bear in mind. The second thing to bear in mind is there are times in maths where you might be faced with an equation where you might notice that something is appearing on both sides of the equation, and therefore you might be tempted to cancel that thing out by trying to divide by that thing. If you're ever in a situation though where you want to divide by something in order to cancel it out, don't. Instead, factorise that thing you're going to divide by instead. So a classic example for that is even something as simple as a quadratic. In this quadratic, it's very easy to look at it and go, oh look, there's an x squared and a 7x. Both those things contain an x, so I could make the equation more simple by dividing both sides by x. But if you do that, you are going to lose some solutions. So don't. Instead, what you want to do is factorise instead of dividing by x. However, reusing the skill we'd already talked about in the previous slide, we are aware that in order to factorize, you need to rearrange to make the equation equal to 0 first of all. So I'm going to move the 7x over to the left-hand side. And now, instead of dividing by x, I'm going to factorize x out of what's there instead. So therefore, x squared divided by an x will be an x, and then minus 7x divided by x is minus 7. And therefore, this way we haven't lost any of the solutions. Of course, you could continue on from there, set this factor x equal to 0, and then the other factor set equal to 0, solve both of them, and you get this final solutions x equals 0, x equals 7. Factorising is not just useful for solving quadratics though. It can also help you solve more difficult equations, like for instance cubics, or higher order polynomials than that, like quartics, quintics, etc, etc. If you want factorising to easily help you, what you're looking for in particular are any of those styles of equations that don't have a constant term on the end. That means they don't have like a +2 or a +5 or a -9, basically some sort of number without any algebra attached to it on the end of the equation. You notice that is the case for the cubic we've got on the screen right now. If that is the case, therefore we can do what I call sort of highest common factor style factorising to your equation, because we notice all the terms in this cubic all contain an x. So again, we could factorise an x out of all of those terms. So therefore I'm going to write an x, and therefore inside the brackets we'll be left with an x squared, a minus 7x, a plus 10, and then we therefore close the brackets and set equal to 0. Then to solve the equation, well, we just set each of these two factors individually equal to 0 and solve those two mini equations to get the solutions. So that means we're going to be solving the quadratic separately, so you can use whatever method you like to solve that quadratic. However, we could actually continue factorising this cubic even more, because the quadratic factor we currently have could itself individually be factorised as well. So we could do that, and therefore we'd get the x that we still had before we're carrying over, and then the factors caused by the quadratic, which would be x minus 5, x minus 2. That's useful because although we've now factorised an equation and got more than two factors, the rule we were using before still applies, which is each individual factor you have can be individually separately set equal to 0 to help you solve the equation, as long as the equation is equal to 0. Once again, reiterating that important point we made earlier. So therefore we separately have x equals 0, x minus 5 equals 0, or x minus 2 equals 0. And those three mini equations are what lead to the three solutions: x equals 0, x equals 5, x equals 2. There you go. And on to an even harder looking equation. This time we've got trigonometry functions involved, but don't worry, if you haven't come across equations that have trigonometry functions involved yet, we're just going to be focusing on how factorising can be used to help start this question off rather than the steps that are after that process. In fact, that might even come to your advantage if you haven't come across the more complicated stuff yet, because it's easy for a lot of students who have learnt that more complicated stuff to start trying to rewrite this equation in unnecessary ways that take far longer, when factorising can simply be used quite early on to make this actually a quite simple equation to solve. Something you do need to be aware of though before we begin is something to do with the notation, which is that sine squared of x thing that's appearing there. You need to be aware that that secretly means sine of x in brackets all squared. I'm aware that notation looks a bit weird and is a bit counterintuitive, but it's just the way mathematicians decided we write this stuff, so it's something we all have to just get used to writing. Anyway, with that said, therefore, because we realise the left-hand side is secretly sine of x times by sine of x, and the right-hand side is sine of x times by cos of x, it would be super tempting to go, oh, I could just divide both sides by sine of x to cancel it out. But we now know better because of this video, so therefore we're not. Instead, we're going to move everything over to one side of the equation. And then instead of dividing by the sine of x, we're going to factorise sine of x out of the entire equation. So therefore, sine squared of x, because that means sine of x times by sine of x, and we've factorised one of those sine of x's out, we're just going to be left with the other sine of x left behind. And then the sine of x cos of x, we've factorised the sine of x out, leaving us with just the cos of x part. And there you go. The reason that's useful is now we can split the equation up into two mini equations. Sine of x equals 0, and then separately sine of x minus cos of x equals 0 as the other separate equation. And what that's done is it's now got two mini equations that you would then solve using the methods that we use for solving equations that have trigonometric functions involved, which is something we cover in a future video. Okay, and on to this example 2. And it's worth pointing out I chose this specific example because I remember an exam question that once involved students having to do a whole bunch of steps that then led to an equation that looked like this. Now, because students had already had to do a whole bunch of steps that required a certain level of difficulty to do, by the time they reached this equation, or a similar style equation to this, because actually in reality the equation had more horrible looking numbers in it, but it had this general structure, because students had already done some fairly complicated math leading to it, and then they were faced with another equation that looked slightly scary, students assumed the scary equation required some more scary maths in order to be able to solve it, when in reality you can solve it just using factorising. So, with that said, another skill you need to be aware of is index laws, because it would be tempting to look at this question and just go, oh, I could divide both sides by 2 to the power of x, because we realize by index laws 2 to the power of 6x divided by 2 to the power of x could then be simplified. And you would be right, but we have been making a good point now that instead of dividing by something to cancel that thing out, it's better to factorize. Admittedly, for this very specific question, you wouldn't actually be punished if you had divided both sides by 2 to the power of x, but that's just because this is a special occasion rather than a general rule, and therefore I'm trying to get you into good habits. So if you want to divide by something to cancel something out, instead factorize it rather than cancelling it out. So therefore I'm going to move the 8 lots of 2 to the power of x onto the left hand side, because then that makes me aware that the 2 to the power of 6x is secretly 2 to the power of 5x times by 2 to the power of x, because in that situation when you're multiplying, it's the same as adding the powers. So that's useful because then that allows us to factorize 2 to the power of x out of the entire equation, which means we're just left with 2 to the power of x, open brackets, 2 to the power of 5x minus 8 equals 0 after closing the brackets, of course, as well. And that's helpful because then we're left with the two mini equations, 2 to the power of x equals 0 and 2 to the power of 5x minus 8 equals 0. 2 to the power of x equals 0 actually has no solutions. If you've done some more complicated maths involving things called logarithms, then you have a way of showing why that is. But also intuitively this makes sense. There's no number we can take 2 to a power of that will result in 0, because we're multiplying basically positive numbers by positive numbers however many times depending on what our power is, and no way will that lead to us having a number of 0. That's not possible. So there's no solutions to that first thing, and then there are solutions to 2 to the power of 5x minus 8 equals 0, because 2 to the power of 5x equals 8, and therefore we know 2 to the power of 3 equals 8, so therefore 5x has got to equal 3, so therefore x equals 3/5. You could, of course, again use logarithms to help you solve that second equation alternatively instead, but that's just another way of solving it if you're a bit earlier on in your maths education. Cool, so therefore, once again, we can use factorising to help us solve complicated looking equations. And to finish the video off, we're going to be looking at a little side note that occurs after students have heard me mention this idea of, oh, if you want to divide by something you shouldn't divide by it, you should factorize it out instead, when it comes to looking at solving trig equations, for instance. Now, this will only be applicable if you have learnt how to solve trig equations yet, so if you haven't done that yet, this specific part of the video come back to at a later date once you've covered that stuff. But anyway, the traditional way of solving this equation is to divide both sides by cos of x. And the reason you want to do that is because if you divide both sides by cos of x, on the left-hand side you'll have sine x over cos of x, and on the right-hand side you'll just have a 1. And therefore that's useful because then by trig identities, you can then simplify this equation to then be just tan of x equals 1. However, some students start to worry that this method for solving the equation is not good because of what I mentioned before about this idea you shouldn't divide by something, you should factorize out instead. However, do listen carefully to what I did say before. I did say that we're only having to worry about dividing by something if you're dividing by it with the intention of cancelling that thing out on both sides of the equation. That's not what we are doing here in this scenario when we're dividing by cos of x. Because although we're dividing by cos of x, which does cancel out the cos of x on the right hand side, on the left hand side there was no cos of x. So we weren't cancelling anything out. And so therefore dividing by cos of x is not an issue. Even when we convert the sine of x over cos of x to become tan of x, that still isn't cancelling out that cos of x, it's just rewriting it in a way that makes it look nice, rather than actually getting rid of the maths that's involved with that cos of x. So it's worth pointing out that this as a method is still allowable, and it's only when you're dividing by something with the intention of cancelling it out on both sides that it becomes a problem. And therefore actually, in fact, for this particular scenario, you actively shouldn't try and factorize cos of x out. Because if you do, you'll create some additional solutions that technically don't exist for the original equation. Because what you'd end up with is you'd end up with sine x minus cos x equals 0, which by itself as a step is fine. But then if you factorize the cos of x out, you'd end up with cos of x, open brackets, sine of x over cos of x minus 1 equals 0, which will get cos of x tan of x minus 1 equals 0, and in doing so, this thing being set equal to 0 would create some extra solutions that shouldn't exist. So therefore, don't do this because you're factorizing something that wasn't there. You should only factorize out something that's appearing as an actual factor in all the things you're factorizing out of. Okay, that's it for today's video. Hopefully you found this video useful for helping you know how to deal with some harder looking equations. Factorizing is basically a very useful tool when used correctly, so use it to help you out in a variety of situations. Okay, see you in the next video. Goodbye.